As we mentioned yesterday with our complex numbers, these imaginary numbers we can't place on the number line. So we have to come up with a different way of representing them graphically. And we call that the Argan Diagram. So every single complex number can be placed on this Argan Diagram. And it looks very familiar. It looks just like the coordinate number plane, which I suppose in a way it is. Except now the x-axis, we think of it as the real axis. So that's the number line that we're used to seeing. And the y-axis becomes the imaginary axis. So all of our purely imaginary numbers would lie on the imaginary axis. So if I wanted to plot 2, same as normal, it would lie on what we're used to seeing as the number line. Now if I've got a purely imaginary one, minus 3i, then it would lie on the imaginary axis. But if I've got one that's a combination, then it really is just like coordinates. So minus 2 and I would be minus 2, 1, we would plot that. If I had 4 minus I, then 4 minus 1. 4 plus I would go at 4, 1. This brings up the first interesting feature of the diagram. Conjugates will always be reflected in the real axis, because the only difference is the sign. One would be plus the imaginary amount, one would be minus the imaginary amount. So it'd always be reflected. What about if I plotted minus 4 plus I? There it is over there. The reason I picked that one is, you'll notice it's 4 minus I multiplied by negative 1. So it's D multiplied by negative 1. And look at the two relative positions of D and F. What happens is they're rotated 180 degrees, or if you like, reflected through the origin. So anything multiplied by negative 1 should be. And that's no different to our normal number line if you think about it. Because if you were going to plot the number, well, there it is there. Let's say we plotted 2. If I wanted to plot negative 2, well, then I would reflect it through the origin and it would be over here at negative 2. If I was to multiply it by I, then it becomes 1 plus 4i. And so now if we look at the relative position of G that we just plotted there, and you'll see it's still rotation. But this time instead of 180 degrees, I've multiplied by 90 degrees. Well, if you think about that, multiplying by negative 1 is like multiplying by I squared, or 2 rotations of 90 degrees, which is why it's reflected 180 degrees. So every multiplication by I will rotate it 90 degrees. The nice thing about the Argan diagram is every point, every complex number would have a unique position. Like us in terms of complex numbers. Horizontal and vertical lines. So there's a horizontal line. Now, when we're talking about coordinate geometry, we'd say it has the equation y equals a constant number. But now we could say, well, that means the imaginary part of the complex number is constant. So the imaginary part of z is constant. A vertical line, similar idea. That one would have an equation x equals k, but x is the real part. So we can say, oh, well, every point on that line would have a real value of k. It'll be k plus some imaginary amount. Circles. Now, we're used to seeing x squared plus y squared equals the radius squared. But remember yesterday we said z times z conjugate was the sum of 2 squares. So x squared plus y squared. So now we could write the circle like that. Z times z conjugate is r squared. So what have we got when we look at this one? Z plus 4i times the conjugate of z plus 4 minus i is 49. Well, I could expand the whole thing out, which I've done. Oh gosh, looks messy. Let's tidy it up a bit. Looks even messier. But eventually we get there, because if I don't know what it looks like, I'll take it back to the x and y's, and then I've got a Cartesian equation, and hopefully I'll recognise it. Now I've got it as x squared plus y squared plus 8x plus 2y. Oh, actually, it's still going, isn't it? We still haven't finished that one. Yeah. Okay, let's get going a bit more. Well, we know it's going to be a circle because of the x squared and the y squared. Complete the square. Eventually we've got it. X plus 4 squared plus y plus 1 squared is 49. So we know it's a circle, centre minus 4 minus 1, radius 7. I could have saved myself a lot of time. Go back to the original equation. Okay, remember we know z conjugate is r squared. All that's happening here is a shift. So Z has been shifted to the point 4 plus I. Oh, sorry, minus 4, minus I should say. So the centre has moved to minus 4, minus 1. So that's really what's happened. And then, of course, over here we get the conjugate of that one because we're dealing with the conjugates. So in fact, if we see that, Z minus some complex number, and then in the other one we've got the conjugate of Z minus the conjugate of that number, we know, yes, it's still a circle, but I've just shifted the centre to whatever that complex number is. Again, not something I immediately recognise when I look at it. So 1 on Z plus 1 on the conjugate of Z. So let's play around with this one and see if we can come up with something. So multiply everything by Z conjugate. Still don't recognise it. So all right, let's get it back to its Cartesian equation. Remember, Z conjugate I know is going to be x squared plus y squared. Z plus Z conjugate, I should end up with 2x because it's going to be twice the real part. The imaginaries are going to cancel. So yet again we've got a circle, sort of. X minus 1 squared plus y squared is equal to 1. Not 100% true that it's a circle, because if you draw it, there's our circle, we've got a little problem. Right? Because according to our picture there and our equation, 0, 0 is a possible point. But if you go back to originally what the question was, it's 1 on Z plus the conjugate of Z is equal to 1. So it's not possible for Z to be 0. So actually, we should exclude that point. So if we were to draw it, we'd circle that point and say, hey, not included, that one doesn't work. That'll do us for today. Only got a single. I know. Just